Good morning and welcome to this class today for Physics 4B. Today's topic is on Faraday Lens Law, okay, and that's chapter 29. Chapter 29 and chapter 30 are linked together, so what I'm going to do is I'm going to do first of all probably one example from chapter 29, but leave the bulk of it for later on for chapter 30, because actually it's only one idea to get together. Faraday Lens Law, which is really the induction of the electric field, which is induced by the magnetic field. So that is the point of it. So at some point today, the lecture might sound a little bit heavy because of the fact that I will be summarizing everything together up to this point of what we know, okay? In a sense that it's a summary of everything, and I will introduce some symbols that may sound kind of a little bit hard to imagine. But the reason why I'm doing that is because I'm really preparing for chapter 32 that is coming down the road, which is a big chapter. So here is how the course is, at least the rest of the course is laid out. Chapters 27 and 28 introduce the magnetic field, really, and how the magnetic field can influence a charge moving in it and can also influence a wire that has a current running through it. So that was actually chapter 27. Chapter 28 gave us Ampere's law, and Ampere's law tells us basically that in order to create really a magnetic field, you need a current. And the way the current is going to be created is that it curls around. I mean, the magnetic field is created, but the current is going to curl around the current. So the current is along the thumb. You have to use your right hand, of course. And the way that the magnetic field goes around, it goes like the palm goes around. So basically, it goes in a circle. So we call this one a circulation. We calculated the circulation of the magnetic field, and we found that it's proportional to the current enclosed. Okay, so there was no current, there is no magnetic field. That is in a nutshell what that means. If the current happened to be going down, then the curling is going to be in the opposite direction. So it was counterclockwise this way, at least from my vantage point. From my vantage point, this will be then clockwise, okay? So this is really how this chapter 28 was. So it gave us basically in a sense, the magnetic field. Chapter 29, which we're about to do it, stem from the following points. Okay, let's go back into what we learned up to this point from chapter 21, from when we first came in. Charges create an electric field. That was actually Gauss's law. So what Gauss's law is saying is that if you have a charge inside in a region of space, it's going to create a charge. If the charge happens to be positive, the electric field will emanate from it in all directions in space, never returns really. It's going to go and then to go to infinity, okay, where it's going to be so small at infinity that it may be taken to be zero. But if it's a negative charge, the electric field will come from infinity from every single direction actually in space and basically stop in it, okay? So in a sense, there is an influx of field lines coming from every direction to the negative charge, and an outflux of field lines going into space, basically from a positive charge, which allowed us to define what the flux is to begin with. So the flux is the measurement of these field lines per unit area, really. So that's why, by definition, the flux is the product of the vector times the area, summed through space. And that space has to be a closed surface for us to account for all the field lines. If it's an open surface, then we're counting some flux, we're counting it, but we're not counting everything, okay? We're just counting for that open surface. Typically, Gauss's law says that the flux of the electric field over a closed surface, it doesn't matter what the shape of the surface is. Could be the skin of an animal, for a goat, for example. You tie it together, and then you find how much outside of the field lines are coming from it. That measures how much charge is enclosed, because the charge enclosed over the epsilon naught is that measurement. Now, that was the first thing that we introduced. So the flux of the electric field, we know it. Now, the flux of the magnetic field has to be zero because of the fact that a field lines that is going to leave a pole, it doesn't matter which, So I have the North Pole in here. So it's going to leave this North Pole and go around. No matter how far it's going to go, it's going to come back at some point and come back to the South Pole. And that is because poles come in pairs. They don't come in single charge. Unlike positive charge and negative charge, which they come in single charges, these ones, they don't. They always come in pairs. So if an electric field is somehow ending in the South Pole, it must have emanated somewhere from the North Pole. So if I'm interested trying to find how much field lines are coming in and out of this space, of the surface, as long as it's closed surface, and count just the field lines, I'm counting them. One leaves and comes back. So at the end, they cancel. So there is no flux for the magnetic field over a closed surface, regardless of where the magnet is. And that is because of the fact that there are no monopoles. So we know the flux of the magnetic field. We know the flux of the electric field. We also define the circulation of the magnetic field as basically the line integral over a closed path. It turns out, by Ampere's law, that that circulation of the magnetic field over a closed path is equal to, proportional to the current that is passing through an area that is closed by that path. That turns out to be Ampere's law. So we know two things about the magnetic field. We know its circulation, which is always zero over any closed surface. We know also its flux is zero over any closed surface. And we know its circulation across any path is just basically a measurement of how much current is enclosed by that path. Also, we know the flux of the electric field is just a measurement of how many charges. Now, we're missing something. We're missing the circulation of the electric field. The circulation of the electric field is zero because of the fact that the flux is always outward or inward for the electric field. So if I go around on any path, it doesn't matter. There is no circulation. It's always pointing outward or inward. It doesn't go around like the magnetic field, okay? And that is basically, in a nutshell, the summary of everything that we know at this point. It turns out, because of the relationship that we already have found, namely the fact that Ampere's law says that a current creates a magnetic field. What creates a current to begin with? It's a difference in potential. And the difference in potential equates to an electric field, because the electric field and the potential are related via the relationship that the electric field derives from a potential. So the electric field creates a current, which in turn creates a magnetic field. This led people in the early 1800s to think maybe magnetic field also will create an electric field, because here is Ampere's law. Electric field creates a magnetic field, albeit indirectly, because the electric field first creates a current, and the current creates a magnetic field. So, could it be possible that a magnetic field also creates a current? So what I'm going to demo for you guys now is that experiment. I'm going to do the actual experiment and show how can I make an electric field, a magnetic field out of an electric field. I'm sorry. That is Ampere's law. So let me recap. So ignore what I just said, okay? How can I create an electric field out of a magnet? That is really what we're going to do. So for that, I'm going to switch cameras, and I'm going to do the demo. So let me change camera. For that, probably I need to, hold on, let me turn on the light, because there is not enough lighting in here. Turn on more light. Because that camera is sitting at an angle where there is not enough lighting coming from it. So I have light coming underneath the screen right now. And so let me switch cameras now. Okay, so what you're looking at, let me move it up a little, is a coil. Let me remove this thing, so I don't need them. You clearly see I've been doing a lot of demos in here. So I have here a coil of wire made out of copper, actually, and this is a protective skin in here. Otherwise, this whole thing becomes just one conductor. Basically, they'll be short-circuited. As a matter of fact, this thing in here is, but that's not part of the conduction anyway, so don't worry about that. So we have a wire that is connected to a multimeter device. And the multimeter device, as you can clearly see right now, is sitting in the low current detection mode. So what I'm going to do, I'm going to move this one to, and I have a magnet. Where is my magnet? I'm going to take a magnet and put it on top of my coil, which is just a wire. So at the end, that's all I have connected. So I'm going to turn on this one to the proper gauge, since I already want it to be in. So right now I'm registering no current whatsoever. So in other words, I have a magnet that does not create an electric field. And I have a wire basically next to that magnet, and nothing is happening. As you can clearly see, the reading in here is shows 0, despite of the fact that I have it in the lowest current possible, which is a microamp. Microamp is 10 to the negative 6 amperes. So right now I'm detecting no current, so it seems to me like it's not going to work. But look at what happened if I take this magnet and move it around, okay? So I'm going to move around the magnet, and all of a sudden I have a current. As long as the magnet is moving in and out, and the sign changes, okay, depending on if I'm moving in and out. Look at the sign before it. I have a current that I'm registering. It can be several hundred actually at times if I do it too fast or too slow, depending on how I'm doing that. I'd have to really do it carefully in order to get any decent reading. But I'm getting at least several dozen microamps, okay? I'm getting a current, as long as the bar magnet in this case moves in and out, okay? In and out of the wire, okay? At some point I'm getting some 90 something, okay? But as long as I'm doing the motion, it's fine. If I stop my tracks, the reason why you see this reading is because my hand is shaking. But if I put it somewhere, there is nothing. And if I put it immediately on top, nothing is going to happen. Okay? If I put it in here, nothing is going to happen. So how about if I do it the other way around? Keep the magnet and move the coil now. So I'm going to do the same thing now, except the coil is moving in and out. It's the same thing. So whether the magnet is moving or the coil is moving, as long as I have some relative motion between the two, it seems like I am recording a current. And that current could only be explained by an electric field. So let me change cameras again. I didn't mean to turn it off. And let me put this thing down. So there is a way for me to create an electric field if the magnet moves with respect to the wire, or the wire moves with respect to the magnet, or both. There is another option that I cannot demo to you guys. Even if I keep the magnet still, and even if I keep the coil still, both of them not moving with respect to one another. If I change the magnetic field in time, if the magnetic field is time dependent, that too will do the same thing, the trick. So what matters really is a quantity that has to do with the overlap of the because I can move the wire actually, and I didn't do that, anywhere in space outside of the coil, and it's not going to do anything. So it seems like the relative motion of the coil and the magnet and how they overlap in terms of magnetic field and coil. That's really what matters, and that needs to change with time, whether by moving one or the other or by changing the value of B. So that turns out to be Faraday's law. So there is a way for us to actually create an electric field out of a magnet, and that is the trick behind it. That is actually behind the power generation for anything in here that uses that you can get electricity for. Your household there uses this principle, use a dynamo somewhere in power plant that generates electricity by making sure that there is a magnet spinning in a coil or the other way around, and that relative motion is really what generates that power that comes to your household. So this is actually the principle behind it. We have electricity at homes. Okay, so let me share with you the screen. We're doing 29. Share. So let me explain where we are right now, where we are. Oh, no, I don't want it to be green. I want it to be a regular color. So the first thing we discovered was Gauss's law. And Gauss's law says the flux of the electric field over a closed surface, this is closed surface, and the circle in here indicates that, okay? Any closed surface is basically the measure of how much charge is enclosed in that surface. So the enclosed in here refers to that surface, okay? So there is a volume that is enclosed by that surface. So you have some sort of a closed surface, and that encloses a volume, and you measure how many charges you have, and that is basically what the law is saying. I'm not going to prove this, but I'm going to tell you how this can be translated into a differential form. If you go in a tiny region of space where there is a charge distribution rho per unit volume, I can convert this expression from being a double integral into a triple integral using basically Gauss's theorem. And this, instead of just being the integral of EdA, becomes the integral of the divergence of the electric field with respect to the volume. And this Q is actually triple integral also over the charge distribution. So both of them become an identity. And since this is true no matter what, that only means that the integrand are equal. So the charge distribution over epsilon naught is equal to basically the divergence of the electric field. So this is equivalent. Okay, and if we are in session, if we are live, we can show that easily how that you can go from this double integral into a triple integral and make this identity. If you're really interested in this one, and this is actually the divergence theorem, so your calc 3 or calc, I don't know, one of the calcs, they do that. So it's called the divergence theorem, and which is Gauss's theorem actually too. If you're interested in a very beautiful demonstration on how it works, you can just refer to Feynman lectures. Okay, and I think I have a link in my syllabus. So this form is a differential form of Gauss's law. So we're basically taking ownership of what we did up to this point in physics. So this is the same thing. So this equation, I'm going to call it equation 1. The reason why I'm calling it equation 1 is because it's a scalar equals to the dot product of two vectors. Remember, the gradient operator is just a vector whose components are the derivative with respect to x, the derivative with respect to y, and the derivative with respect to z in the I direction, in the j hat direction, and the k hat direction. Okay, so you can form a dot product and think of this one as some sort of a dot product of two vectors. One of them is an operator, the other one is just a vector. Okay, so this is the same thing. This is Gauss's law. So as I warned before, this may sound a little bit heavy, but don't really think too much about it. Just think of in terms of what we learned in this class, in terms of Gauss's law. But I will need this format down the road, so probably I will use it. Okay, I'm not sure 100%. I can still use the integral form if we have problems with this differential form. So this is law number 1 that we learned. Law number 2 basically is similar to this one. It says that the divergence of the magnetic field over any closed surface must be 0, and there are no. The reason why that is because there are no monopoles. Monopoles. That's why. I mean, if there are monopoles, then this integral could just be the measurement of how many positive or north poles and how many south poles, or add them algebraically and divide by or multiply by some number in here. Okay, so again, this is any closed surface, whether there is a magnet in there or not, doesn't matter. Permanent magnet or an electromagnet, it doesn't matter. So this one equates to, using the same theorem as mentioned before, as a divergence of B is equal to 0. In other words, the magnetic field never diverges. It always circulates. basically starts at some point and come back to its tail. So its head is somewhere in here, and then no matter how far it goes, it's going to come back and touch head to tail. So it's going to be back on itself. So that is what this expression means. On the other hand, this one is suggesting that the electric field always diverges, emanates from this forms in here. This is, you have to be careful with this one. This is true only in the case of electrostatics. This two, I'm going to call it equation number 2. Both of them are the same thing, by the way. These two forms, one of them is an integral form and the other one is a differential form, and they're the same thing. Okay. What we learn also from Ampere's law says the following, that if I have a magnet in space and I want to find the magnetic field, I should say, in space, and I would want to find the circulation of the electromagnetic field. So this is on any closed path. This is a line integral, is equal to mu naught times the current enclosed by that path. So you have a path, it doesn't matter what the shape of it is. So you go into the region of that and see how many currents are going in and out of that.
Professor, something happened.
Yeah, I'm sorry, guys. I don't know what happened. In a long time, this thing did not happen. So for today, we lost connection. It came back immediately.
Yeah, right down as you went down to the next thing you're about to explain, you froze, and then the whole thing just crashed.
Okay, so let me share with the. Did we get into Ampere's law?
Oh, no, I think that's what you were about to explain. That's where it cut off.
Okay. So Ampere's law basically was basically tells us how the magnetic field circulates. I mean, yes, circulates. Because if I take any path that is closed path, okay, like this path that I'm trying to describe in here. So if I measure how many currents are coming in and how many currents are coming out, and add them algebraically through that area that is enclosed by that path, okay? Then I have a measure for that circulation. So this is the circulation, basically, and I'm how defining it. Because remember, just we argued that the magnetic field does not diverge, which means it could circulate, and this is its circulation, actually, okay? So we know everything about the magnetic field because we know how it goes around and we know how it diverges, which it does not. Then we have everything that we need, and this stuff is actually borrowed from hydrodynamics, so it's really a good, useful thing. So I don't know if did you guys have fluid mechanics? Oh no, actually that's part of physics C, part C. Anyway, the point being in here, and even then we don't go into a lot of details of this thing because hydrodynamics is one of the most complicated sciences that require most complicated engineering classes that require some work in here. Anyway, so the point being in here is this is how the magnetic field circulates using something called Stokes theorem. What we can do actually, we can define the current density just like when we did way back in chapter 25, namely the current density is just this, the current is just the sum over the area of the current density, basically. So the current basically will be just the integral of JDA. Okay, so that is a current flowing through this area S, if you want to call it that way. And if you do that, so this is an area integral, so this is two integrals, okay? Whereas this one is just a line integral. But Stokes theorem, what it does, it takes this integral and converts it into a double integral, similar to what we did with Gauss's law. And then you will have a surface integral and a surface integral over the same surface are identically equal all the time, only and only if their integrands are the same. So it turns out, if you do that, the curl of B will be pulled out of that. So the curl of B which is just the cross product of this same operator, del operator, that's called del sometimes, or the divergence operator, okay, crossed with the magnetic field itself. So this is a vector, must be equal to mu naught times J. So this is equivalent to this expression, but actually in a differential form, that's all. So this is actually equation 3, but don't let this equation to fool you. Actually, it's 3 equations by itself, because this is a vector relationship, and the vector relationship has 3 components, and regardless of what coordinate system you're using. So there are actually 3 equations there and there. And now we're missing a piece of the puzzle. We know how the magnetic field circulates. Here it is. We know how it diverges. Here it is. We know how the electric field diverges, and here it is. We don't know how the electric field really diverges, if it does at all, okay? Technically, according to this expression, it doesn't, but I just showed that there is a way for me to create an electric field that goes in a circle, because it starts from some point in here, in the wire, and goes through the wire, comes out of this node, goes through the multimeter, comes out from the other side, and closes on itself. So basically, this is a circulating electric field, and that is the one that is created by the magnetic field. So magnetic field can create a circulating electric field for me, and that is the whole essence of Faraday's Lens Law. So let me demonstrate this one graphically to see what's going on, and I'm going to write it down, and that's going to be actually 3 more equations, in addition to a very, very useful and important relationship that we know. And that is basically, once we find the electric field, I can find its effect on a charge. And once I find the magnetic field, I can find that effect also on a charge. And this is, of course, the Lorentz force. Obviously, this is not just one equation, it's also 3 equations, because it's a vector equation, and vector equation has 3 components in the x direction, the y direction, and the z direction. That's if they are using coordinates system of that. So once you do that, you have to use F equals to ma, and F equals to ma is actually 3 equations also, and so on and so forth. So basically, we would have everything if we know the missing part in here in this equations. So let me do an experiment in here. I'm on the screen to explain what happened in there. So I have a magnet. Let's say, for example, the magnet is pointing into the screen. So think of this magnet as north is this way, pointing into the screen. So the field lines are going into the screen and probably ending somewhere else, or coming from the other side of the galaxy and hitting the magnet that I am pointing in here on the back of it. Okay. All of this is just representing the field lines of the magnetic field, that's all, in space. And think that I have a wire. So I'm going to draw a big wire in here. I'm going to draw it. No, I'm going to draw it. So what I have now, I have a wire partially immersed into a magnet. And the other part, there is nothing else other than the light and a light bulb. So think of this one as some sort of a light bulb, okay? So there is no power, there is no energy, there is no battery. Yet, if I move the wire into the screen, what happened in this case? With the velocity v, this way, I will see that the light will go on, as long as it's partially immersed into a magnetic field. If it's fully immersed, no, there will be nothing, even if as long as you're moving with constant speed, okay? So v is assumed to be constant. If it's not completely immersed also, there will be no light. Move it this way, there will be light. Move it that way, there will be light, as long as it's partially immersed. So it seems like what matters really in the whole deal is this region of space, where there is an overlap. As long as there is an overlap, you're good, okay? So what's going on in here for the charges? So if I look at the charges on an individual basis, this charge in here is not inside the magnetic field. So I cannot write QV cross B because B is equal to 0 in this region of space. But in here, B is not equal to 0. Since this charge is moving with the wire, this charge is moving this way, and the magnetic field is pointing into the screen. So if I apply Lorentz force QV cross B, so what's going on in this case is V is pointing out this way, B is inside the screen, so there is a force that is going to be pointing upward. So this charge will try to come out of the metal, come out of the wire. Assuming that the wire is rigid enough so that this does not happen, so the charge cannot come out of the wire, basically. Same thing. This charge also, that is sitting in here, is moving in this direction. That's its V. Its magnetic field in that region is pointing into the screen. And again, it wants to come out this way too. But again, assuming the same assumption that those charges are, those wires are rigid, so nothing is going to happen. So that does not explain why the light goes on. But look at this charge in here, any charge in here, sitting in here. This charge is moving this way with the wire. It's inside a region of magnetic field that is pointing into the screen. So now there is a force that tries to push it upward in this direction. And there is room for it to move now because this is a conducting wire, and conducting wire charges can move. Since that charge wants to move, this charge also will come and replace it because also it's under the same constraint. This charge that was sitting in here finds an empty space in here because, again, it's a conductor. So it's going to move and replace that charge. And then it's going to move in the same direction. This charge will replace this one, and this one will replace this one. And in actuality, what I have, this one actually will move because of the same reason as the other two in here that were on this side. That's being replaced by the one that moves into its place. So it's going to come in here and replaces the one that has moved upward. And this one replaces the one that has moved upward. But this one now finds the charges in here in its place, its path. So if it wants to move in here, this charge better get out of the way and move in here, okay? So this charge in here better move and make room for this one that moved in its place, and so on and so forth. And you can clearly see that there is a current that is going to flow in a conductor without the battery, without any battery whatsoever. And this current is going to go counterclockwise. So that is basically what's going on. If I move the wire in the opposite direction, it's the same thing, with the exception the force is going to be pointing down, so the current that is going to flow then is going to be clockwise. That's all, okay? So now I have an knowledge of what's going on. So let's see what's going on in that region of space. First of all, the force that is responsible for this motion is QV cross B. The EMF that caused that wire to go, that light bulb to go on, is by definition the work done by a unit force on a unit charge. Okay, across the entire closed path. So this is what the EMF is. This is the electromotive force. So what the electromotive force is, how much energy a force on a unit charge does. So Q is equal to 1. Okay, so the force then is going to be equal to QV cross B everywhere in here. Okay. In here, there is no contribution. First of all, the motion on this path is along this direction. So this is, again, I'm going to write this one. So I'm going to define this one as QV. I'm sorry, it's V cross B. What am I writing in here? The Q is not a charge. Q is equal to 1. So I'm going to write this one F1, by the way, because I need to emphasize the fact that this is a unit charge. Crossed, dotted with DL. That is what the circulation in this case is. So it's the circulation or the work. This is a work, force times displacement, okay? So this is DL. This is where the force is. And there is a cosine of 90 degrees between them. So there is zero contribution to the work in here. So this zero energy in here for this entire region of space. There is zero contribution in here. because of the same thing, because the force and the displacement are perpendicular. There is zero contribution in all of this region of space because B is equal to 0 there. Because this part is 0. So the only place where I have a displacement in this direction and a force also on a unit charge in the same direction where the angle between them is 0 degrees, that is in that contribution in that region. And the force there is constant. I mean, I drew it a little bit jaggedy, but I was not trying to do so. It's because I cannot draw vertical lines on this screen in here. So the thing with it is, so I have this force times this displacement, and that is going to be FDL. Even if it's jaggedy, by the way, the contribution that are perpendicular will cancel for the same thing. A reason that this canceled because they will be perpendicular, and the only one that is going to stay positively contributing is the one that is in this direction. I'm going to assume that the width is W and the length is L, okay, of this wire. So in this case, what matters is not the entire L. What matters is just how much of the wire is immersed at all. So I'm going to call this direction X, okay? And the rate at which X is changing with time is actually the velocity, okay? So this V, the same V in here, okay? So that is what that is. So what looks like this expression is F1 now, which is constant, and F1 is going to be in magnitude, V is in this direction, the magnetic field into the screen, so they're perpendicular to one another, so that it involves because this is where V is. The magnetic field is going into the screen, so there is a 90-degree angle between them. So when I do the cross product, it's going to be V times B times sine of 90 degrees, which is just 1. So in this case, the force is involved as sine of 90 degrees. So the force will come out of the integral times the length of the path, because that's the integral from this point to that point, which is just W, the width of this wire, that's all. So that is how much integral you have. So the force now, if you want to write it, it's actually VB times W. But V, if you remember, is just the derivative with respect to t of x times BW. And B and W are constant. Both of them are constant. The wire is not changing shape, and the magnetic field is not changing in magnitude. So I'm going to pull them inside and write this as the derivative with respect to time of just B times W times X. And W times X is this area, the shaded area in red. That is the crossover area. That is the overlap area. And this is a magnetic field times an area, and the magnetic field times an area, because the area I'm going in that direction. So it looks like this is just a dot product. This is the flux, actually, of the magnetic field in that area. So what this looks like is then it's the derivative with respect to time of the flux of the magnetic field in that area only. Well, if you say, okay, forget about it. I want to find the flux for the entire loop. Well, it's still the same value. Why is that? Because in here, the magnetic field is 0. The magnetic field is not 0 in the case of the overlap. So it doesn't matter really. So this is the flux of the magnetic field in that entire region of space, including the overlap region where it has a finite value. And in here, it's 0 because B is 0 itself. So as long as this quantity changes with time, I have an EMF. Okay, I know and you know that the electric field is the one that causes charges to move. Okay, because we did that way back in chapter 27. We said the magnetic field does not really do work. The magnetic field, all it does, it bends charges, that's all. So there must have been created an electric field that causes all of these charges to move, and that has been created by this changing flux of the magnetic field. So what's going on then is this EMF in general is actually defined as the circulation of the electric field over a closed path. And because Q is equal to 1, so this is actually still the force on one charge. And this, in this case, I'm going to leave space in here because I need to talk about the sign now of the magnetic field. Okay, the sign has to be negative, and I will tell you why. Okay, let's look at what's going on in here. The flux of the magnetic field, when the wire is moving this way, is increasing into the screen. In other words, when the wire moves this way, I'm sorry, when the wire moves in this direction, it's going to account for more and more field lines. Right now there are 1, 2, 3, 4, 5, 6. And then next time this one will go in, this one will go in, and this one will go, there will be 9. Next time there will be 1, 2, 3, 4 more lines, so on and so forth. So as the wire is moving more and more this way, it's taking more and more field lines going into the screen. But the current that is going on, the current is actually going in the counterclockwise direction. If this current creates a magnetic field, its own magnetic field, and it does, because it's a current, and current always creates a magnetic field per Ampere's law, per this law. This one, okay? So if this creates its own magnetic field, this current itself, that's what's generated now, that made this light bulb to go on, can create its own magnetic field. That magnetic field, because the current is going, actually curving counterclockwise, its magnetic field is coming out of the screen, actually, not going into the screen. So the magnetic field that was created now, pointing in this direction. So this is the induced magnetic field due to the induced electric field, due to the induced current, because the wire is moving, the area is changing. That's really what's going on in here. So it's clearly that magnetic field is opposing to the magnetic field that created it. So it's really biting the hand that fed it to begin with. So here is a magnetic field minding its own business, pointing into the screen. If the wire moves or the magnet moves, it's going to create an electric current or an EMF at least. Okay? If that EMF can create a current, and it does in this picture because we have a light going on, then that current will create its own magnetic field in such a way its own flux is making up for the flux that is being changing. So the flux now is going more and more into the screen. This flux that is created actually for the magnetic field, that is induced, is out of the screen. So I say in this case, the sign better be negative, because if this flux is increasing in one direction, it's decreasing due to the induced current that is being created. So this sign has to be negative. You say, okay, what happened if the wire is moving in the opposite direction, actually moving out of the field lines? Then in this case, you're encountering less and less charges in this case, less and less, field lines. So what's going on in here, the current is going to flip, of course, you know that, because the direction of the force will go in the opposite direction. So the current will be actually in the opposite direction, and it will be clockwise. And a clockwise current will create a magnetic field pointing into the screen. So there are less and less field lines coming into the screen. So it's going to make up for the ones that are being lost by pushing its own into the screen. So it's always negative. Whichever way the flux is changing, it's going to make up in the opposite direction for where it's changing. So it's really a big thing in here, this minus sign. This is due to Lenz. The actual law is due to Faraday. And this law now has a name. They call it Faraday Lens Law. Faraday Lens Law. Okay. Len's contribution was about that sign business. Okay. So let's put it in words so that you guys, if the magnetic field flux, remember, this is not the magnetic field that we're talking about. This is the flux of the magnetic field. And the flux of the magnetic field in general is similar to the electric field, is the integral of BdA. This integral better be open, because if it's closed, we know that the flux over a closed surface is going to be 0. Okay, so this is the flux of the magnetic field. If the magnetic field flux, and this flux magnetic field, by the way, has a unit, separate unit, because of its importance. The units for the flux of the magnetic field is the Weber. Okay, so that's something that we sometimes refer to. If the magnetic field flux changes with time, it induces a circulating electric field whose circulation, hence circulation is actually the EMF, whose circulation, namely the EMF, electromotive force, is the rate at which the magnetic flux is changing with time. This is something that you really need to write, okay? And at least say once, because it's not over yet. This is just half the story. We have to talk about that sign, okay? The direction of the EMF is such that if it can, which is not guaranteed all the time, by the way, drive a current. So if it cannot drive a current, you assume that, let's close it and see if it can drive a current. So we'll see how it does it. If it can drive a current, that current creates a magnetic field whose flux compensates for the changing flux. Of the magnetic field that created it to begin with. This is a mouthful. This is a big, big thing, okay? This summarizes everything, all of the observations that we know. So you need a magnetic flux that changes with time. If it's not changing with time, and it changes with time in one of three ways, actually. Either the loop moves in a magnet. If it moves in a magnet, the area is changing with time. Since the area is changing with time, now the flux is changing. Or the magnet moves with respect to the loop. That too will result in the same thing. The overlap region between them will change with time. Or both of them don't move, but the magnet changes with magnitude. So there are more field lines going in or less field lines going in, or more field lines coming out or less field lines coming out in time. So, or the combination of two or more of the previous ones. So all of this could result in a changing flux. So if that happens, then there is an EMF that is going to be created, end of the story. Okay. Now you would want to know, of course, the EMF is equal to the rate at which that flux is changing with time. So it's easy. Most of the time, what we do in the algebra, we just take the EMF as just the absolute value of everything and solve for it, okay? Now, the important part of this side is not really finding the EMF. The EMF is actually easy. Just take the derivative with respect to time of that flux, okay? It is really the sign business that really has to be careful. Almost, and I'm not guaranteeing this one, but probably you might be careful with the next exam that you're going to be hit with this kind of questions. You will be asked to find directions because even in an entry level of an upper division course in physics, or sometimes even in a graduate level, where you're going to be asked something like this, I mean, similar to this fashion, to find the direction of the EMF. So the direction of the EMF, which is really the headache most of the times. How am I going to find it? Look. See where the flux field lines are changing. If they're increasing in one direction, you have to choose a sign for the EMF in such a way that EMF, if it can drive a current, because sometimes you have an open loop, so it's not going to drive a current. So it's just going to be a pile up of charges on one side and a depletion of charges on the other. So in this situation, close that loop and see which way the current is flowing. That current needs to flow in such a way to compensate for the changing field lines. So if they're increasing in one direction, you need to make them increasing in the opposite direction. if they're increasing in the opposite or decreasing in that direction, so you'd want to increase them in that direction. So that is really usually where the headache is, trying to find where the sign is. Okay. See where the field lines are changing, are going more and more in, so you need to bring back a little more and more out. And you have to bring them at the same quantity, as a matter of fact. If 10 field lines were inside, and all of a sudden you see 12 field lines going in, you need to bring 2 more out. Okay. Now, if there were 10 going in, but now only 8 are going in, so you need to push 2 more in with the way that you have to choose a current in. So that is really the headache with this law. So let me rewrite it in its full glory. Faraday Lens Law. Again, the circulation of the electric field. This is what we were missing, actually. The circulation of the electric field over a closed path, any closed path, is equal to minus the derivative with respect to time of the flux of the magnetic field. I remind you that the flux of the magnetic field, again, is written as the surface integral over a closed surface. I mean, not closed surface gives you 0. Of a surface, the surface must be enclosed by that path in here. No, there is an overlap. I'm sorry, there is an overlap, unlike the other one in here, of BDA. But that is what the flux of the magnetic field is. So again, using Stokes' theorem, we can take this path integral and convert it into a surface integral, the same surface integral here where the overlap happens, and then require that these 2 integrands must be the same. When we do that, when we use Stokes' theorem, this becomes just the curl of E, and this becomes just the minus the derivative of the integrand, which is just minus, because B could potentially depend on space, so we have to take the partial derivative. So this is another way of writing Faraday Lens Law. Either you write it that way or this way. This is the integral form, and the other one is just the differential form, okay? So it's using the same trick. So now we know how many equations are this? It's 3 equations, by the way, because it's a vector relationship. So this is everything that we know up to this point. Okay, I know it's heavy stuff, and I mentioned and I warned you guys before that it's going to be a little bit of heavy stuff in here. Okay, so how can we make this? I mean, we can talk about the power generations and the AC circuit at this point because we're almost there, and we can have stuff like that. But I'm going to delve right into one of the problems that we're going to look at, and that is problem 59 from the book. And you will see problem 59 in the book is a hard problem, and it's not hard because of physics 2. It's going to be hard because of physics 4a, okay? Not because of 4b. So let me get into the book. Let's see if we can get into chapter 29 from the book. And looking at problem 59, okay? So what problem 59 has in here is the following. It has a loop. Let me draw it a little bit thin. It's actually not a loop. It has a wire like this one, open wire. Oh man, I cannot draw this. Can I draw this? Yep. Okay. So that answers that. And this wire is here. Too big. That's good enough. I didn't mean to create too big. Now let's run this wire this way. So it's open on the other side. There is nothing connected to it. In the same time, I have actually another wire. Let me draw it thicker, which is like this. So this second wire is in here. And this one is the one that has a finite mass and so on and so forth. So let me make it slightly smaller. This one has a finite mass, and we can talk about this one in here, okay? So you have of length L. So the length in here, from here to here, is L. this length of the wire L, okay? And it has a mass M, okay? We're getting ready to use F equals to MA because of the mass, inertia M. A uniform magnetic field in space is shown. So basically you have a magnet that is also into the screen. So everywhere now in this region of space, there is a magnet pointing into the screen, similar to what I was describing earlier. So you have a magnet in here. That is, its north is pointing into my screen in here, okay? And the wire, so there is a B field in here, okay? The wire is given in initial velocity, as you can clearly see from the picture, pointing in this way. So there is an initial velocity V naught in this way. Obviously, this will change with time, so this wire will move, and then it does, this surface, the overlap surface again, will change with time. So this surface will change with time. There will be more and more field lines enclosed by this one in here. And as it does, the wire at some point will be in here, and its velocity will be probably changed as a function of time, some velocity. It may be more or less, depending on the physics of the problem, than what the other one is. So that's basically the setup of the problem. And they tell you specifically, there is no friction between the slide wire. So this is called a slide wire. So that's when they are talking about slide wire. That's what they are referring to. So this is your slide wire. This one, okay? So there is no friction between the slide wire and the loop, and the resistance of the loop is negligible in comparison to the resistance R of the slide wire. So there is a finite resistance in here, R, and the wire itself has a negligible resistance. R is practically equal to 0 for the other one, okay? So the question is, show that obtain an expression for F, the magnitude of the force exerted on the wire while it is moving at speed V. So at some point it's moving with a speed V, which is not the initial velocity V naught, so it's some other velocity. So we want to find the force exerted on it. So it's several cross products, and you have to be ready for them. That involve chapters 27, chapters everywhere, okay? This chapter also. So the first thing that we need to do in order to find the force is find the current that is flowing through this wire. If we find the current that is flowing through this wire, then we're going to use chapter 27, where we found the force on a wire that is carrying a current, this expression. Okay, we know its length, it's L. We know the magnetic field is given. So if I find the electric field, the current that is running through the wire, I am in business. So let's go back in here. So I need to find the current that is going to be flowing. So first of all, I need to find its direction. The area is increasing this way, correct? There are more and more field lines going in. So in order for me to compensate for the ever-increasing field lines into the screen, I need to create field lines coming out of the screen. So the magnetic field that is going to be coming out need to have a current circulating counterclockwise. So the current that is going to basically emerge from this one is this current, basically, and that current has to be pointing in this direction. And this is the current I. Because there are more and more field lines as this wire is moving in this direction, and the field lines are going into the screen. So the magnet that needs to be created, or the magnetic field that needs to be created, need to be pointing out of the screen to compensate for the increasing one that are going into the screen. So this is just fresh from what we learned today. Okay, so that's its direction. So we took care of the minus business. There is no need to plug in any more minus, because the minus, all it does, it gives me the direction of the electric field. So this is how you solve problems with Faraday's Lens law. So the first thing is try to find the direction. Once you do that, you do not try the minus anymore. So we already know. So this is equivalent to a battery, basically, that looks like this. So I have a battery that is pushing a current whose EMF is equal to the derivative with respect to time of the flux. That's all. Because I really don't have a battery in here. I really have a wire, and that wire, the flux of the magnetic field is changing with time. So I have an EMF in here. So in other words, I'm taking this one in absolute value because I know the direction now. And I have negligible resistance. The only resistance that I have in here is this R. So we're back into some chapters 25 or 26, where we have an Ohm's law, and Ohm's law tells me in this case the current I, this is R. Ohm's law tells me that epsilon is equal to Ri, and so this is Ohm's law now. And Ohm's law will give me the current, which is just the EMF over R. However, I need to use chapter 29 to find what this EMF is. Well, the flux of the magnetic field is going to be just L times B times the width, in this case, which I'm going to call X. And X is changing with time. So the flux of the magnetic field would be simply equal to the magnetic field times the area. And the area is L times X. And I need to take the derivative of this flux with respect to time. B is constant. L is constant. The only thing that is changing is X, and that is V. Its derivative is V. So that is the EMF. So that gives me the current now. So the current, so this is Faraday Lens law. Faraday Lens law also was used to find the direction of this current. So the current then is equal to, when I combine the two, is BLV divided by R. So this is the current now. I have an expression for the current. And the current, as you can clearly see, is pointing out of the up in the screen. Now, this is what I have now. I have the current going up, so that's the direction of L. And they have a magnetic field that is going into the screen, so the force that is going to result from it is going to be on the opposite side. So this is the force actually that is going to be coming out in this case. So let me use this color. So this is the force F using the cross product, because F is given by the current times L crossed with B, where L has the same direction as the electric current. See how useful that Lens law is, the minus sign business? If we didn't know which way the current is flowing, I wouldn't know where the force is pointing. So now I have L pointing up, the magnetic field into the screen, so the force now needs to be opposite to the velocity. So the force is actually a negative value when it comes to the acceleration. So if this particle is moving this way, it's going to be decelerated by this force, okay? So the magnitude of this force then, if I sub everything, everything is perpendicular to everything. L and B are perpendicular especially. L is on the screen, whereas B is into the screen. So the angle between them is 90 degrees. Sine of 90 degrees is 1. So this force is going to be equal to, in magnitude is ILB. And I know its direction now. And I just found it using Ohm's law and Faraday's Lens law, combination of the two. So this is actually, in a sense, is Lorentz force. So this is, we derived it for using Lorentz force. Okay. So now we have I, which is BLV over R times LB. Well, the L and the B are already in the expression, so the force is going to be B squared, L squared over R times V. So this is the force that I want us to show. So this is part A, okay? So this is physics 2. We got everything that we need. Part B, show that the distance x traveled by this wire moves before coming to rest is this expression. They gave you a very long expression to show the displacement. Now I have to invoke physics for A. I have a mass for the wire, and it's moving this way, and I have a force opposite to the direction of motion. So if I apply Newton's law in this case, in this direction, in the x direction, so there is only one F equals to ma in this case, and the F is going to be equal to minus this expression, B squared L squared over R times V is equal to ma, and A is just the derivative of V with respect to time. This is an expression that I can integrate. All we have to do is manipulate stuff. So what I'm going to do for this expression, I'm going to multiply by dt and divide in the same time by m and divide by v. If I do that, the v on this side cancels, and the dt will come in the numerator, and the m comes in the denominator. The dt will be canceled from this expression because I multiplied by dt. When I divide by m is gone, and I will be left with a dv over v. Okay? Technically, this operation is not permittable, terms of purely calculus, but you have to go to the finite variations and take that limit, but we can assume that we did that. So we're going to have dv over v, if we do that, dv over v, I'm sorry, not dv over t, dt, is equal to minus b squared L squared over mr times dt. Now I'm going to integrate both sides. I know this is going to be an independent integral, so I'm going to integrate from t equal to 0, where the velocity was actually equal to v naught, to some t, where the velocity is some v as a function of t, okay? So in other words, I'm trying to find the antiderivative of this expression knowing the initial conditions. Well, the integral of dx over x is just the natural log. So this is the ln of v evaluated between v naught and some v, which is some function of t, is equal to minus the integral from 0 to t of dt, and that is going to be just t, okay? And the natural log in this case, the upper value is ln of v, and the lower value is ln of v naught. So this will become ln of v as a function of t minus ln of v naught is equal to minus b squared L squared over mr squared, mrt, I'm sorry, okay? There is a property that you guys have discussed when you were doing the natural log. Ln of the difference of two arguments, or the difference of the two ln's is just the ln of the ratio, a over b. The sum is just the product of the two quantities. So this is part of the properties of the natural log. We can write this expression as ln of vt over v naught is equal to minus b squared L squared over mr times t. Take the exponentiation of both sides. The exponentiation cancels the natural log, and I will just have the ratio of v sub t with respect to v naught is equal to the exponential of minus b squared L squared over mr t, okay? In other words, v sub t as a function of t, we found the velocity as a function of time to be simply v naught times exponential of minus b squared L squared over mr. So in other words, this rod velocity will change from the initial velocity that we gave it and decays exponentially until it reaches 0. So when does it reach 0? When t goes to infinity. So when t goes to infinity, this velocity will reach 0. That is the property of the exponential. So they told us to find the distance traveled when it comes to a stop. And it's not going to come stop anytime soon. It's going to come to stop after a long, long time. So we really need to find that overall distance. For that, we have to integrate this expression. Mind you, that all of this calculation is for physics 4a. All of the work in terms of physics 4b is done up to here, okay? So we're not done yet with the part B until we do this last part. So again, we know that the velocity as a function of time is dx over dt. That means that x traveled between the initial position and the final position. So this is the actual displacement. This is what they are asking us, is the integral from the start, which was at t equal to 0, to the end when it comes to rest, which is t equal to infinity. That one is going to come to infinity of v dt. Okay? And I have v, I just found it. It's that exponential form. So all I have to do is just integrate the exponential. So the x of t, x, not x of t, this is the finite value. So this is a bounded integral from 0 to infinity to exponential of negative b squared L squared over mr t dt. So basically I sub the value that I have in here for this velocity. Now the integral of the exponential is the exponential itself. Basically we know that the exponential of minus at dt is the antiderivative is my negative 1 over a exponential of negative at. Because if I take the derivative, I will find that same expression. The negative cancels the negative and the a cancels the a, and you will be back to the exponential. So what I'm going to do is invert this expression. So it's going to be negative mr over b squared L squared times v naught. And the integral is going to be just the exponential. So x now is going to be minus mr v naught over b squared L squared. If you are familiar with physics 4a, if you remember it, this is actually the angular momentum of that of a particle of masses. I'm sorry, That's nonsense. I have to divide by some radius of curvature, and I really don't have any linear circular motion. I'm sorry, my brain drifted a little, okay? Ignore what I just said. This is not true. This is actually a resistance. This is an ohm, okay? I'm sorry, the integrated expression now is just minus b squared L squared over mr t 0t. It's sometimes good to really have your brain drift a little so that to see if there is a meaning in here that is emerging from an expression, okay? But in this case, it's not, okay? This is actually the regular linear momentum. mv squared is mv naught is actually the linear momentum, not the kinetic energy, the linear momentum, okay? So in other words, b squared L squared divided by r, that must be some sort of a momentum of some sort, albeit it's a magnetic momentum in this case related to the magnetic field. So let's find the limit. The limit for this one, the upper limit is actually infinity. So the exponential of negative infinity is 0. The exponential of 0 is 1. So we'll have 0 minus 1 times this expression. So it's going to be a negative times negative, and it's exactly what we need. So x is equal to mv naught times the resistance divided by b squared L squared. This is the distance traveled by the wire before it comes to rest. This expression. And if you look at the expression here that they tell you, show that it's exactly how they want us to show it, okay? This is the exact same expression that we have in it. This is a very useful expression, as a matter of fact. And I know that we're probably, no, we still have time, still have time. This is a very useful expression because it tells us a way of finding the magnetic field, actually. If I know the initial momentum of the rod, okay, mv naught, and if I know the resistance of the rod, which I can use an ammeter like this one and find it, actually, this is an ammeter that can measure the resistance, okay? And, excuse me, if I know its length, a ruler will give me that. And if I can measure how far it traveled before it came to a stop, I can measure the magnetic field. So this is a clever way of doing things and finding the magnetic field. So let's discuss this problem and see where the difficulty is. And I took it in purpose because I wanted to see everything in here. So what I have in here is actually F equals to ma. That's Newton's law. Newton's second law of motion. So this is Newton's second law. So what we have in here is the following. These are just integrations, stuff that has to do with integral and antiderivatives and things like that. And we even took advantage of this expression at the end to find a way of measuring a magnetic field in a region. For example, if I want to try to find the magnet, how strong this magnet is, I could do the same experiment in here. As long as I have a rod and this one can contain the entire rod, I should be able to do it. Obviously, this is not big enough, but this magnet is probably good enough for that experiment as long as I can find it, okay? Even its finite displacements, I can do that too, because I can use the properties of the exponential. And if I can measure the distance traveled, then I'm in business, okay? So I don't have to integrate from 0 to infinity and wait for it to come to rest. I can just integrate from over 1 second, for example, and do the same expression and how I can find x. And knowing that, I can do this integration and find the magnetic field, the strength of a magnetic field. So this is taking advantage of a problem, basically, and finding a way of doing things. Now, let me discuss the problem again, okay? It's very important. So what we started with is this setup for the problem. And we said that I need, if you are asking me the force, I need to know the current that is flowing this one. We just came from a class where we know that if the flux of a magnetic field changes over a region, I will have an EMF. And as a matter of fact, I will have a current in this case because it's a closed loop. Since it's a closed loop, current will flow through it. So I need to find that current. I better do. Because if I do, I use Ohm's law. Basically, I write the equivalent circuit for it and just find the current. Current is just the EMF over R, where R is the resistance of this wire. Okay, because the other resistance is negligible. So now we have the flux, and the flux is just the area times the magnetic field. The magnetic field is constant. The width of the rod is constant. The length of this loop is changing, and it's changing at the rate of V. That is the rate at which the entire flux is changing, V times B times L. So that is the EMF. Now we have the EMF. We divided by R. We found the current. We go back all the way to chapter 27 to this expression. And all we have to do now is find the cross product, find the direction of the force. And once we find the direction of the force, we have the current, we have B, and we have L. So all we needed to do is find this direction of the force and plug in everything. So indeed, this is exactly what we used. Everything is perpendicular to everything, so we don't worry about the sign, but we worry about the direction. The current is going up, the magnetic field is going in, so the force is actually impeding the motion of the wire. It's trying to prevent it from going any faster. It's going to slow it down, actually. That is really what the Faraday Lens Law is. It's used, among other things, for slowing down things. It's really negative effects, like friction, really. And because it opposes direction of motion. Had we started with this problem in the opposite direction, had the rod was moving this way, the force will be actually in the opposite direction, trying to slow it down still, similar to friction. It opposes direction of motion. This is the essence, this is the roots of the so-called eddies that form when a magnet is moving in a region of space, and usually that is an undesirable effect, okay? I have made a video actually for last semester's class, and I'm going to share with you guys for how the eddies form. And I have a rod in here, and I have all of the equipment for it in here and a magnet, and you can clearly see that the magnet slows down when it's going through a rod. And there is no forces in it whatsoever. All you need is just a metallic rod. The rod I have is made out of copper, and then it goes through and it slows down. So that is, in a sense, what's going on in here. So it's like slowing down in motion. So we have the force. The force is directly proportional to the velocity, just like the viscosity from your class from physics 4A. Viscosity also is proportional to the velocity, and you oppose it to it in direction. Always, whichever the direction of V is changing, this one slows it down. And now, that was the bulk of it. Honestly, if you really think about it, this is not really hard stuff. The only thing that is hard about these things is these cross products. You have to keep track of them. Okay, once you have that mastered, this part is not hard, okay? It is this part that is hard. This is physics 4A. Then you apply F equals to MA and do the integration and remember the properties of the log. Then you do another integration and remember which boundaries you're going to integrate, because the problem was not clear from where, tells you until it stops. You need to find when that happens, and that happened to be t equal to infinity. So that's what dictates your boundaries of integration. And if everything went all right, you should prove what they ask you to prove, okay? So hopefully this problem was insightful enough for you guys to see how this thing works. I promise the problems are not going to be that hard when it comes to doing problems like this ones. You will have chapter 30, which we're going to start actually on Thursday. In chapter 30, we'll take advantage of Faraday Lens Law again and invent a new device for us, in addition to all of the devices we have discovered so far. We know about the battery, we know about the capacitor, we know about the resistor. We know now we're going to discover a new device this coming Thursday, and that device is going to be the inductor, which will put us in a very good shape for AC currents and AC circuits, especially the RLC circuit, resistor, inductor, capacitor, and how important those play in terms of resonance and in terms of electronics in general, okay? So if you're curious, and I know we still have about 2 minutes, if you're curious trying to see where is an inductor in a wire, where is this thing is applied, if you look at any electronic device, this bulky thing, actually, that's where Faraday Lens Law is. This is transformer, actually. And that's going to be our topic for next time. For next time when we meet again, wherever there is a coil, you know that there is actually Faraday Lens Law. So there is a coil in here, there is a coil in here, there is a coil in here, and there is a coil in here, and there is a coil in here. Most of the time in electronics, you will find only one transformer in it. That is usually near the power supply. There is another transformer in here. Isolated by itself, actually, I moved it, okay? There is a primary and secondary, and usually there are 4 legs in it, some for the input and others for the output, the primary and secondary. But this device is unique because so many of them, because it takes advantage of what I mentioned in the lecture, namely the oscillators. And because this is actually this is like for a TV, for a signal reception and emission and things like that, as you can clearly see from this coaxial cable that is going into it. And there's actually an HDMI port to it. So it uses so many of them because it wants to get so many different frequencies. So this is not just for power generation, as it typically is, like for this electronic device. Okay, so we are out of time. I'm going to see you guys on Thursday. I know some of you applied for that grant, and we're going through the process basically of selecting a few people, and hopefully you will hear from us very soon. Okay, thank you. Let me stop the recording.